Hello, Algebra 2 Trig students. We are back in action with Unit 3 of this year. So Unit 3 is about polynomial functions. We just finished a unit on quadratic functions, right? And so that was relative to this graph right here. Well, y equals x squared, or you could put f of x equals x squared. It was a parabola. So now we're going to extend this and we're going to study cubic functions, y equals x cubed, or f of x equals x cubed, or quartic functions, or quintic functions, or etc., etc. So x to some power. What you have studied in Algebra 1 back in the day was constant functions, where y just equals some number, like if this was 5 right here, or you've studied linear functions, where y equals mx plus b, right, or y equals 2x plus 3, or something like that. But again, this unit is on polynomial functions. So polynomial functions, how do you know if a function is polynomial? Well, the graphs will be smooth and curvy, so you won't have any pointy tips. So you might think of like an absolute value, right? An absolute value graph is like a V, right? It has a point there. So a cubic function or a quartic function or a polynomial function will not have that. The graphs need to be continuous, so you can't have any breaks, gaps, or holes in the graph. And they need to go on infinitely, so go on forever and ever, so therefore we put arrows on the ends. Okay, so here's a little chart to introduce some different aspects of these graphs. Specifically, we're going to focus in on the degree of a polynomial, right? So your degree of a polynomial, it says the degree of a polynomial function is equal to the highest power exponent on x in the equation. For example, every quadratic function has a degree 2 because it's x squared. The degree of a polynomial tells you the maximum number of x-intercepts the polynomial could have. Therefore, the polynomial of degree n has n roots, or n x-intercepts, and only if these roots are real, then it will have that number. Actually, that's not true. It always has that number, but some of the times they can be imaginary, and sometimes they are real, or you can call them not real and real. So looking at this chart right here, this table, it says here you have a function y equals k being a constant or a numerical value, so this is called a constant function. It has a degree of 0, which means it should have 0 intercepts, right? So graphically, what did that look like? You saw that on the top of your page, right? This is your constant going through here. The only time it would have infinite intercepts if it was actually the x-axis, if it was y equals 0. Otherwise, it's going to have 0 intercepts. For a linear equation, right, this is a linear equation, y equals mx plus b. It has one x-intercept or one root, right? It's going to intersect the x-axis at one point. A quadratic function has x to the second power. It therefore has a degree of 2. And therefore, the maximum number of times it can intersect the x-axis is 2 times. If you have something to the third power, we call that a cubic function. It could have a degree of 3, or not could have, it does have a degree of 3 because that's the highest power. And therefore, it could have a maximum of 3 intercepts. If I'm looking at that graphically, I could go 1, 2, 3 times it could intersect the x-axis. If you have x to the 4th power, 4 is the highest degree. This is called a quartic function. It has a degree of 4, and that means it would have a maximum of intersecting the x-axis at 4 times, so we could make it look like a W, and go 1, 2, 3, 4. And then we could keep going and going and going, right? We could have x to the 5th power, x to the 6th power, x to the 7th power, and we would just keep going. 5 times it would intersect the x-axis. 6 times it could possibly intersect the x-axis. 7 times, etc. Okay, example number 1. It says, determine which graphs below represent polynomials. If the graph is a polynomial, determine the possible degree of the function. If it's not a polynomial, then say why not. So I think you should pause, try this on your own, look at the definition of polynomial, look at all the different things we've talked about, how you would find the degree, and then come back and look and see if you got the answers correct. All right, you should have said this first one is a polynomial. It's smooth and curvy. If it goes all the way through to the end of the graph, that means it is going on infinitely. Looks like it's intersecting 1, 2, 3, 4, 5, 6 times. So that means it should have a degree of 6, right? Because it crossed the x-axis 6 times. And yes, it is a polynomial. Letter B is not a polynomial. Why is it not a polynomial? Because it ends, right? So this doesn't have a domain that goes on infinitely. It stops, so it's not a polynomial. C is a polynomial. It only intersects the x-axis at one time, so it has a degree of 1, and it goes on forever and ever. It's just linear, right? Letter D is not a polynomial because it has this sharp turn. So not a polynomial because it has a sharp turn. It looks like a absolute value to me, which is not a polynomial. Letter E is a polynomial. It intersects 1, 2, 3, 4, 5 times, so it should have a degree of 5, and it's smooth and curvy and goes on infinitely. And letter F, because it stops before the graph ends, it means it does actually stop, and it has these hard turns, right? These are pointy, hard edges, a hard turn, so this is not a polynomial. All right, moving on. It says the equation of a polynomial function can be a monomial, a binomial, a trinomial, etc. So now we're changing it. This is our information about the number of terms that a polynomial has. So poly is many, right? So it's many terms. So if it's a monomial, it just has one term. If it's a binomial, it has two terms. Terms are separated by plus or minus signs. The trinomial has three terms. So an example of a monomial would just be x. A binomial would be x plus 2. A trinomial would be x squared plus 2x plus 3. Right? So three terms or two terms separated by plus and minus signs. The exponents or powers on x have to be whole numbers, not fractions or negative numbers. The coefficients have to be real numbers. They can be integers. They can be fractions. They can be irrational. They just have to be real. So they can't be the square root of a negative number. It says determine which equations below represent polynomials and which do not. If it's a polynomial, identify what type of polynomial function it is. Is it a monomial, binomial, trinomial? So in other words, how many terms it has. And then if it's not, state why not. So I would pause, try this on your own, and then check back when you're done. All right, here is what you should have gotten. Excuse me, I think I said you had to decide if it was a monomial, binomial, trinomial, which was actually false. It just said what type of polynomial function it is. So that is it a quadratic, is it a cubic, quartic, linear, etc. So anyway, look here. A, C, and D were not polynomials. So you can see here x to the 1/2 and square root of x is the same thing. So those are not polynomials because this is a fraction exponent. So the exponents or powers have to be whole numbers, not fractions. Well, those both represent fractions. Then this one doesn't work because it's a fraction itself, actually, and we can't separate it into making it whole numbers, or we can't separate it. So this is a rational function because it's a fraction, so it's not a polynomial. So this one is a polynomial. If you were to FOIL this out, expand it, you would get a trinomial or a quadratic function. And this is already an expanded form. These are fine, these coefficients. It says our coefficients can be integers, fractions, or irrational. And x to the 3rd power is the highest degree, which is 3, so it's a cubic function. Okay, moving on. Example 3. It says consider the graph of f of x equals x cubed minus 7x squared plus 7x plus 15, which is here off to the right. State the degree of the polynomial. Well, the degree of the polynomial is just the highest power, which is 3, so it has a degree of 3. State the domain. Well, if it goes on infinitely, it's going to continue to get wider, going to the positive infinity and negative infinity, and it has to continue to go up and continue to go down, because you can see that here, the end behavior, so it's going to be from negative infinity to positive infinity. So your domain and range are all real numbers, or negative infinity to positive infinity. The x-intercepts we can see it has 3 x-intercepts. The x-intercepts are -1, 3, and 5. And so how would we write that equation in intercept form? Well, we have some stretch value. We don't know what it is, but we have our 3 intercepts, and remember, you write them with the opposite sign. So if it's a -1, we should have x plus 1 in parentheses, x minus 3 in parentheses, and x minus 5 in parentheses. This letter A, we would have to find that stretch value, and eventually we'll do that as we continue through this lesson, right? And we have to have some other value on the graph in order to help us find that A value. So we don't know exactly what this is. I can guess and tell you it's 15, and so this means when I plug in 0, I'm going to get 15 as a result. So if I plug in a 0, a 0, and a 0 for x, I should get 15 for y. So it's 0 plus 1, and again, we're going to focus on this later, 0 minus 3, and 0 minus 5. Well, 0 plus 1 is 1 times -3 times -5. That turns into positive 15, so we get 15 equals a times 15 divided by 15, and a actually equals 1. So the equation, we now know that a equals 1 is f of x equals 1 times x plus 1 times x minus 3 times x minus 5. And that is it. Okay, how about this next one? You might want to pause here and just try it on your own, right? So I would completely try it on your own, pause, see how you do. We'll go from there. All right, did you get, for example, or for part A, has a degree of 3, again, because of this leading exponent is 3, the highest exponent is 3, degree of 3. The domain and range are all real numbers, or -infinity to infinity. You can see it has an x-intercept at -2, 1, and 3. And here is what I would get when I put it in intercept form. Now it looks to me like if you put in 0 for x, it looks like we would get positive 6, is that right? And so we want to get maybe a -6 this is supposed to be, we're not sure, so maybe a is -6, but again, we'll worry about that later when we give you more information. But it says, describe how the cubic function with a positive leading coefficient is different from a cubic function with a negative leading coefficient. Well, yeah, if this has to be -6, 2 times -1 times -3, when I put in 0 for x, right, I'm going to get 2 times -1 times -3. That gives me a positive 6. But clearly this is a negative y value, so my a value must be negative. So I must have a negative leading coefficient. In my previous example, we had a positive leading coefficient, and the graph looked like this. So if you were reading this graph from left to right, you would be walking up the hill, right? So it would be up, and it would be increasing at the end. If you have a negative leading coefficient, which a has to be a negative value, then you start from left to right going down initially, and you end going down. So the leading coefficient being positive or negative does impact the graph. Okay, let's look at example 5. Again, you might want to pause and do this on your own. You have the basic knowledge to kind of get it in intercept form and see what happens, so go ahead and try it. Okay, if you did this on your own, you should have gotten a degree for the polynomial to be 4. Why is that? Well, because it crosses the x-axis at 4 places. The domain is -infinity to infinity because this graph will continue to get wider and wider for every new x value. But the range was a little tricky. We didn't give you this specific value right here, right? So I'm just guessing. This is -10, right? -20 would be down here. So I'm just guessing -13. If you had -12, -13, -14, something, you guess -12 point something, that's fine. But notice I have inclusive because it is actually going to hit that y value, and then it's going to go up infinitely. So that's for the range. Your x-intercepts were clear, -2, -1, 1, and 3. So we have our x-intercepts. Your intercept form should be quite simple. We're always going to be asking you guys to write these equations in intercept form. So that gave us an x plus 2, x plus 3, x minus 1, x minus 3. Those are all factors, or sorry, those are all factors that are going to be multiplied together to give you that function, but we don't know the a value. We do know the a value is positive. How do I know the a value is positive? Why? How do I know that? Well, this y-intercept, right, when x is 0, y is a positive number. So when x is 0, right, so 0 plus 2 is 2, 0 plus 1 is 1, 0 minus 1 is negative 1, and 0 minus 3 is negative 3. And when I multiply those four numbers together, I get a positive result. And if I get a positive result, that means my a value has to stay a positive number because I want that result, my y value needs to be positive. So therefore, a is positive. And notice what's happening when a is positive. This end behavior, it's opening up. It's an even degree, like a quadratic, right? When we did y equals x squared, it was an even degree. It had a positive leading coefficient, it opened up. If it has a negative leading coefficient, what is going to happen? Well, hopefully you're saying to yourself, it is going to open down. So your graph would look something like that instead. Right, so it's very similar to your quadratic. If you have a positive leading coefficient for an even function, or an even degreed function, an even degree, then it's going to open upward. If it's an odd degreed function, that was the one before, or if it has a negative leading coefficient for an even degree function, then it has to open downward. All right, let's talk about end behavior. So we'll expand more on end behavior when you get into pre-calculus, but this is just an introduction. So end behavior of polynomial functions. It says the way a function f of x behaves for very large values of x or for very small values of x is called end behavior. To determine the end behavior of a polynomial function, we look as far to the left of the x-axis, so that's as x approaches negative infinity, or we look as far to the right of the x-axis, or as x approaches positive infinity. So here, if I'm looking at this, this is saying as x approaches negative infinity, right, these values are getting more and more and more negative, then what is y doing? Well, y, or we could put f of x, is approaching negative infinity as well. So as x gets more negative, y is also getting more negative. Then over here, as x approaches positive infinity, what does the y value do, or the f of x value? It also approaches positive infinity. So this is the way we would write, instead of me saying, you notice I'm saying the arrow right here means approaches. So it's as x approaches negative infinity, then f of x will approach negative infinity. So these are arrows right here. So here, I want you to identify the degree and then to describe its end behavior, but we'll go ahead and do this together. So the degree of this first one, it only intersects the x-axis 2 times, but the maximum it could intersect, so what if we'd shifted that graph down, right? So we could have had it intersect 4 times, so it actually has a degree of 4. But 2 of the roots are imaginary roots, so that you're going to learn more about that when you get into pre-calculus. So here it has a degree of 4. What is its end behavior? Well, as x approaches positive infinity, so as x gets bigger and bigger and bigger, what does my y value do? Well, it also approaches positive infinity. As x approaches negative infinity, so as x approaches negative infinity, what does the y value do? Well, it actually still approaches positive infinity. So that's my end behavior. Try letter B on your own. So letter B, did you get a degree of 4? Here I drew this line through here, right? So it could intersect a maximum of 4 locations. If I had shifted that graph up or down, or up, I guess it had to be. So it could intersect at a maximum of 4 places. It only intersects twice, but we'll find out why later. End behavior, here I did the red, as x goes to positive infinity, y goes to negative infinity, or in the blue, as x goes to negative infinity, y also goes to negative infinity. So both end behaviors are going down. And then why don't you pause and try C and D on your own. Okay, look at these last two. Did you get this answer? This letter C has a degree of 3. Again, what are the maximum times it could cross an x-axis? If I drew that x-axis in there at a different place, it would be a maximum of 3. So it has a degree of 3. And then we say as x approaches infinity, y approaches, or p of x approaches negative infinity. So right and down, or left as x approaches negative infinity, p of x is approaching positive infinity. And letter D, we had a degree of 5, and then positive infinity, negative infinity, negative infinity. So my end behavior is here. Okay, so to summarize what we just did, the big idea. For extreme values of x, a polynomial behaves like the highest power term. So what do we mean by that? Well, example 7, it says describe the end behavior of the function f of x equals 3x to the 7th plus 5x to the 4th minus 4. I don't know what that graph looks like, but I do know the highest power term is x to the 7th power. I also know it has a leading coefficient of positive 3. So if I take an x, so now I want the end behavior. So as x goes to positive infinity, what's going to happen to the function? And as x goes to negative infinity, what is going to happen to the function? So as x goes to positive infinity, if I put a positive number in here for x, a positive number raised to a 7th power, is it still going to be positive or is it going to change to negative? Well, it's still going to be positive. The leading coefficient is also positive, so positive 3 times some positive number to the 7th power is going to end up being a positive result. So I know it's going to end as x goes to infinity, y goes to infinity, it's going to end by going upward. Now, as x approaches negative infinity, if I take a negative value and plug it in to x, right, well, a negative raised to the 7th power, a negative raised to an odd power, that's negative 2 7 times, so that's going to leave you with a negative result. So that's going to be negative, but this negative value times a positive leading coefficient, negative times positive, leads you with a negative. So as x goes to negative infinity, my y value is going to be decreasing. So in general, you can sketch your graph however you want. I mean, we don't really know what that graph looks like, but it could have more squiggles in there. But we do know it's going to be a downward trend as x goes to negative infinity and an upward trend as y goes to positive, or sorry, as x goes to positive infinity. So that's it. That is the end of the lesson. We introduced end behavior, talked about the degree, the polynomials. So have a go at the lesson homework, at the assignment, and see how you do. And of course, always ask your questions to your teacher if you have any. Bye.